Okay. So now we'll be discussing about the design of rectangular footing. So let me first read out the question. What is the question? Design a footing of uniform thickness for a reinforced concrete column of size 400 mm by 600 mm, carrying an axial load of 1500 kilonewton. Okay. So here they are using N20 grade concrete and Fe415 steel, and the safe bearing capacity of soil is 200 kilonewton per meter square. So when you see the given data, what and all they have given? Axial, um, axial service load. That is the axial load on the column is 1500. And what is the size of the column? They have mentioned here is 400 by 600. So length is 600 mm and width is 400 mm. Oh, sorry. Sorry. So size of the column here, if you see, length is 600 mm and dimension width is 400 mm. Okay, and SPC, safe bearing capacity of soil, is 200 kilonewton 10 per meter square, and FCK, grade of the concrete, is 20 Newton and FI is 415. So since it is an rectangular column, and moreover, whenever we design any kind of structural elements, we mainly focus for the economical design. Okay, if you consider the economical design of footings, so it should be provided. So whatever the projections you are providing from the face of the column to the end of the footing, okay, that should be equal on all sides. As we discussed in the class, it should be from the all the sides. It should be equal. Okay. So what is the first step? Step one is size of the footing. So size of the footing. So first one, what is the formula we'll be using? Load on size of the footing is equals to load acting on the column by SBC of the soil. Once if you take the total load on the column, you need to consider whatever given load P plus 0.1 times of P. Okay. So why this? We are also considering self weight of the footing. Okay. So if we are seeing the area of the column, total load is load acting on the footing is 1500. So 10% is 150 kilonewton. So total load will be 1500 plus 150. Total you get 1650 kilonewton divided by SPC is 200, right? So you get area of 8.25 meter square. As I said in the class, if you take to the near to the 8.25, what is the value? What is the value you'll be getting? 9. Okay, 9 meters square. Okay. So what is the, like, if you take the root of this, you get 3 by 3 as the value of 9. Okay. So let us consider one side as 3 meters. Let me consider larger length as 3 meters. Okay. And I said the point, and here also it is mentioned. Open if the projection of the footing from the face of the column in both the directions should be same for the economical purpose. Okay. So I know what is the length of the footing I am providing. What is the length of the footing? 3 meters, right? So from 3 meters, if I consider 3 meters minus what is the size of the column? Largest dimension of the column is 600. So that is 0.6 divided by 2 gives you 1.2 meter. That is the projection I am providing from the face of the column to the end of the footing. Can you see the drawing? Otherwise, I'll rub all this so that it will be easy. So here you can see this is the length 1.2 meters. So you can confusion that 1.2 meters is the length. Okay. Now I know this is 3 meters. I know, right? And I know what is the projection length 1.2 meters and projection. Now I need to find what is the total width of the footing. Okay. So I know 1.2 plus 1.2, both sides the projection I am providing. Both the sides 1.2 1.2, right? So remaining, what is this? Sorry. This is 1.2 and this is 1.2. So 1.2 plus 1.2, 2.4 plus what is the width of the column? 0.4. So total you get as 2.8 meters as the width of the footing. Okay. So here we'll be going with the area of 2.8 by 2.8 by 3 meters. So you get an area of 8.4 meters square, which is more than 8.25 meters square. Okay. So this is your first step. And when you take the next step, what is the next step? Step 2 is upward soil pressure. Okay, so upward soil pressure, how you will be calculating? QU is equals to factored load, PU divided by area of the footing. What is the area of the footing we have provided? 8.4 meters square. Okay, and factored load, we need to consider factored load. So given load is 1500 kilonewtons into 1.5. So you get 2250 kilonewtons. So soil pressure at ultimate load, QU is equals to factored load divided by area of the footing. So area of the footing is 3000 by 2800. So you get a soil pressure, upward soil pressure QU as 0.268 Newton per mm square. Now this is your step 2. Now coming to the step 3, depth of the footing from bending moment consideration. Okay, so if you see the drawing here, so bending, it acts as a beam. Sorry, cantilever slab. It acts as a cantilever slab. Okay, only the critical section, you take it as only this portion for the bending moment calculation. So if you see the formula for that, so what is the formula? Mu is equals to QU into L into B, capital B minus small b divided by uh, 8. This is not whole square. Capital B minus small b whole square divided by 8. This is the formula. So once if you have calculated in that formula, you know what is Q value and what is L. So L is a larger dimension. This is 3 meters, right? So 3 you have considered, you have converted into mm. And if you calculate, you got it as 578.9 into 10 power 6 Newton mm. Okay. So you can also calculate in the form of the formula QU into L into length. What is the projection length? Whole square divided by 8. Okay. So in that also if you calculate, you got the same value 578.9 into 10 power 6. Now what you are assuming is mu is equals to mu limit you are assuming. You are considering it as a balanced section and you are finding what is the maximum uh, depth you can provide. Depth you can provide, you are calculating. So what is mu limit value? You have calculated only mu. So you are equating it to mu limit. So you have got 578.9 into 10 power 6 is equals to 0.138 into 20. 20 is grade of concrete and width you will be considering is the larger dimension of the footing. 3000 here, 3000 L you will be considering into d square. From this formula you will be getting what is the depth need to be provided in the point of bending moment. Okay, so if you consider for the shear, so the depth need to be increased. Whatever the depth you have got for the from the point of bending moment, that depth need to be increased. Why? Because if you just calculate with the 264, you further checks, whatever you'll be doing checks for the shear or one-way shear or two-way shear, it might not be safe. Okay. So in that point of view, you need to increase the depth values. Okay. Here I am providing 500. I have started with the 500 value. Okay. So step 4 is reinforcement calculation. You know from the mu is equals to 0.87 Fi ASTD into 1 minus Fi AST by FCK BD. So you get this formula from the annexure G, okay, from the page number 96 of IS 400, IS 456 2000. Okay. So from this, if we calculate, I have got AST value of 3422.9 mm square. I am considering 16 mm dia bars. I will go to the next page. Now I'm providing now I'm calculating spacing of bars. S is equals to small AC into B by capital S. Here I'm considering B value as length of the larger length, larger dimension provided in the footing. So S is equals to, I got 176. So I'm considering 175 mm center to center in both the direction I'm considering. Okay. Now step 5, if you see, check for one-way shear. So check for one-way shear, where it will be acting. If you see, from the face of the column at a distance of D, whatever D you have provided, from the distance of D onwards, the critical section for the shear, one-way shear, it will be considered. Okay, so if you have calculated that distance, I would have got as nearly 700 mm I have got here. So what is the depth I have provided? 500 mm depth I have provided. Thickness of the slab, thickness of the footing as 500 mm I have provided. Okay, so I need to calculate what is the shear force acting on this particular section I need to calculate. So you have the formula for factored shear force, QU into L into whatever the projection length minus thickness of the footing. Okay, in that value, if I calculated, I have got 562,800 Newton or 562.8 kilonewton you could have got. Now I am calculating nominal shear stress. Okay, so tau V is equals to VU by BD. So I have got the value of 0.375 Newton per mm square. Now I need to compare this value with tau C value from the table 19. Tau C value you will be getting from table 19. So for that, first you need to calculate what is the percentage of the steel. So I have got 0.23% for 0.23% and a grade of M20. I got tau C value as 0.35, which is not satisfied. Tau C value is less than tau V value. So it is not safe with respect of one-way shear. So what I'm doing here, again, I'm changing the design parameters. I cannot change the width value, right? Sorry, length of the column I cannot change. What I need to change is depth value. So I have increased to 50 mm, extra 50 mm. So I am providing 550 mm. So VU is equals to, so again I'm calculating what is the shear force acting, total factored shear force. I have got 522,600 newtons. So tau V value I got 317. Now I have calculated what is the PT value. I got 0.21 as percentage of steel. So for that percentage of steel and the grade of M20, I have got tau C value as 0.33 from table 19. So this is safe. So whatever the depth I am provided, even 500 couldn't satisfy the one-way shear. So I am providing the extra extra depth to satisfy the shear conditions. Okay. So now if you see the step 6 is check for two-way shear. So the critical section is at a distance of d by 2 from the face of the column as shown in the figure. So before that, you need to consider what is the perimeter of the critical section. Okay. So I have calculated how you'll be calculating perimeter at the distance of d by 2 from the face of the column. So this is your perimeter. So I have got a length of 4,200. And what will be the area? Perimeter area will be for area of critical section will be perimeter into thickness, whatever the thickness. Here thickness I am providing 550 mm. So now what is the two-way shear stress? First I need to calculate what is VU2. That is total shear acting on that portion. So I have got 1958.4 into 10 to the power 3 newtons. Two-way shear stress I need to calculate. VU stress is equals to load by area. So shear force acting on that critical section divided by area of the critical section. So I have got 0.85 Newton per mm square. Now I need to calculate permissible punching stress, tau P value is equals to 0.25 into root FCK. This is fixed. So you cannot change it. It only depends upon the grade of the concrete. Tau P is equals to 0.25 into root of FCK. I have got the value of 1.12 Newton per mm square. So always the permissible punching stress should be more when compared to the two-way shear stress. This value should be less. So we need to check the condition whether tau P value is more than two-way shear stress or less than two-way shear stress. Here the condition is less than. So it is safe. If not, again you need to change the dimensions. Whatever the dimensions here, perimeter considerations, everything need to be change. Now, if the last step is step 7, it's check for development length. So, what is the condition is the development length, whatever you have got, that should be within this value. Projection of from the face of the column to the end of the footing. That is the projected length. If it exceeds more than that, again you need to change the parameters of the uh, footings. Okay. So I will be calculating LD is equals to development length is equals to 0.87 F5 divided by 4 tau BD. Bond stress I will be getting from the table of from IS 456. Okay. Tau BD is equals to 1.6 into 1.2. So I have got 1.92 Newton per mm square. Additionally, 60% is added for deformed bars. So I have got development length as 752.2 mm. Okay, length available beyond the column face, if you see, that is 1200 mm, which is greater than 752. So hence it is safe against development length also. Okay. So now if you see the last, this is the reinforcement drawing. So I have only just shown the elevated portion. Okay. So I haven't had drawn the plan of the reinforcement. Okay. In further classes, we'll be discussing about how we'll be. So this is the bars. How you need to calculate what is the spacing we have provided. 170 spacing, center to center spacing we have provided. And what is the 175 we have provided. And dia of the bars is 16 dia. And what is the depth we have provided? Effective depth as 550 mm and cover as 50 mm. This is your column dimension. Reinforcement column dimension is here is 400 mm and overall length width of the footing is 2800 mm. Okay, so this is all about the rectangular footing. Is it okay?